Advanced civilizations explore the galaxy, but a Kardashev 3 civilization sculpts and rebuilds it. The Kardashev scale, first proposed by Soviet astronomer Nikolai Kardashev in 1964, is a way of categorizing civilizations by their energy use. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 captures all the energy from its star. A Type 3, it uses the energy output of an entire galaxy. The original scale stops there, though later extensions have proposed Type 4 and beyond. In today's episode, we'll be examining what such a civilization might look like, not just in terms of raw energy consumption, but in its infrastructure, strategy, and scope. What kind of megastructures would a Type 3 build, and would they even need to look like anything we would recognize? We'll explore both the technological and civilizational challenges of reaching that level, including two key paths to K3, one where faster light travel is possible, as in classic science fiction, and one where it is not, which is what science fact tilts toward. Along the way, we'll look at the titanic engineering projects that could emerge, like harnessing not just a single star, but vast swarms of stars, building entire planets from scratch, or things that make planets look small, compacting galaxies to cut down travel and communication lag, or even tugging whole galaxies back here to keep them from flying over the cosmological event horizon. But before we dive into travel and governance, we need to understand what a galaxy is, energetically speaking, and how you begin to claim one. The power of a galaxy. A typical galaxy like our own Milky Way contains between 100 and 400 billion stars, ranging from tiny red dwarfs to brilliant blue giants that shine a billion times brighter than the faintest stars. Collectively, these stars emit between 10 to the 36 and 10 to the 37 watts of power, a few trillion watts. It's a figure so immense that even a Dyson sphere begins to look modest by comparison. In fact, the Milky Way releases several hundred times more energy every second than Earth has received from the Sun in its entire 4.5 billion year history. To call a civilization Type 3 on the Kardashev scale is to say it has found a way to use most, if not all, of that energy. That does not necessarily mean capturing every photon directly. It may involve harnessing select stars through highly optimized systems and transmitting that energy across vast distances using interstellar relays. It could also mean tapping into exotic matter of stellar remnants like white dwarfs or neutron stars, or extracting rotational energy from the supermassive black hole at the galaxy's core. And of course, doing any of that means building infrastructure on a truly galactic scale. We usually imagine a Type 3 civilization as a meta-civilization rather than a coherent one, a loose network of independent systems or small clusters rather than a unified galactic empire. After all, how do you maintain cultural or political unity across 100,000 light years, with communication delays measured in millennia? But today, we'll be exploring options for how such coherence might still emerge, not just in civilizations with faster light capabilities, but even among those limited to sublight speeds. In either case, reaching that level requires engineering efforts that make building planets or even englobing stars look like child's play. You might begin with Dyson swarms around individual stars, vast constellations of satellites collecting energy, but a Type 3 civilization would not stop there. It would likely go on to design and reposition stars themselves, assembling optimized constellations across entire regions. Imagine a galactic orchard of tailored red dwarfs, minimum mass, ultra-efficient stars, bred or engineered to burn steadily for trillions of years. Stars not just harnessed but cultivated. A Dyson swarm of stars, not around one, but made of millions of them. Compact artificial red dwarf galaxies, called Galaxies. This might sound unappealing at first. After all, we tend to think of red dwarfs as dim, reddish stars, and the most minimal mass red dwarfs emit almost entirely in the infrared, which is not really ideal for photosynthesis or power generation. Yet they are still white light sources, producing a spectrum not unlike that of an old incandescent bulb. Moreover, we have techniques for altering their light output, such as star boosting, a method where mirrors are positioned above the star's poles to reflect light back onto its surface. This can raise the star's temperature slightly, shifting more of its output into the visible range. It also spreads that Earth-like spectrum over a broader equatorial region. Or with enough mirrors and fine-tuning, we could shape the spectrum to match whatever conditions we desired. Stars under 25% the mass of the Sun are considered ideal for long-term energy output because they are fully convective. Their interiors churn like a pot of stew, constantly mixing hydrogen fuel from the outer layers into the core. This allows them to burn nearly all of their hydrogen over time, unlike larger stars, which develop stratified layers that trap unburned fuel. In fact, many larger stars only burn through 10% or less of their total hydrogen before evolving off the main sequence, sometimes explosively. The smallest red dwarfs, such as M9 types, with roughly 8% the mass of the Sun, have a luminosity of just 0.0003 times that of the Sun. By contrast, mid-range red dwarfs around 25% solar mass, such as M4 and M5 types, shine with about 0.0078 times the Sun's luminosity. If you're curious, our quarter-mass star has a luminosity of 3 times 10 to the 24 watts, or 6 microwatts per kilogram, while our 8% star comes in at 12 times 10 to the 22 watts, with a power-to-weight ratio of 0.76 microwatts per kilogram. That power-to-weight ratio, or more precisely power-to-mass, is critical for moving stars using stellar propulsion methods like the Shikata thruster, and tend to revolve around letting that star push itself using the power it generates. And smaller stars will accelerate much slower, but also achieve higher final speeds as they burn a bigger portion of their hydrogen fuel. But our 8% and 25% of solar mass stars both use all their mass eventually, and our interest in them here is which packs better. Now, there are two major issues when it comes to packing stars densely. First, all that light and heat needs to be radiated away at a low enough temperature that nearby environments, whether inhabited by humans, alien biology, or artificial minds, do not melt under the sheer thermal load. Second, once you start cramming enough mass, you have to worry about crossing the threshold into becoming a black hole. For example, if we took all the baryonic matter in the Milky Way, hydrogen, helium, and everything else except dark matter, somewhere between 50 and 150 billion solar masses, and compressed it into a single volume, the resulting Schwarzschild radius, or event horizon, would fall somewhere between 1,000 and 3,000 AU. That bigger value is about a tenth of a light year in diameter. A 3,000 AU wide bubble, 3,000 times Earth's orbit, would be over 70 million times Earth's width, and have a surface area about 5 quadrillion times larger. That scale will be important when we return to Birch Planets. And that's just normal matter. Add in the galaxy's dark matter, or start throwing in neighboring galaxies, and the radius grows rapidly. Black holes, after all, double in size whenever their mass doubles. In this case, that's the absolute tightest we can pack that mass before it collapses into a black hole, and you want to stay comfortably short of that threshold. Time also begins to slow noticeably near such immense concentrations of mass. But let's imagine we stay well below that limit and instead use 100 billion solar masses of material to build stars. What would that look like? You could create about 400 billion of the larger convective red dwarfs, M5 class stars, or approximately 1.25 trillion of the tiniest M9 red dwarfs. The total luminosity of the M5 version would be about 1.2 times 10 to the 36 watts, slightly dimmer than our current galaxy. The M9 version would be about a ninth of that, roughly 1.35 times 10 to the 35 watts. More useful though is the total stellar luminosity compared to our Sun. The M5 compact artificial red dwarf galaxy, called Galaxy, would shine with 3.1 billion times the Sun's output, while the M9 called would be around 400 million times brighter than the Sun. Taking the square root of those brightnesses gives you a rough idea of how tightly you could pack the stars and how far out from them you need to be to receive Earth-like sunlight. For the M5 card, that's about 56,000 AU, just under a light year. For the M9 card galaxy, it's closer to 20,000 AU, or about a third of a light year. Pack them any tighter and you burn to a crisp before you got anywhere near forming a black hole, though not by much. That's why we're not even bothering to calculate for even dimmer borderline brown dwarfs, sometimes classified as M dwarfs, the biggest of which do give off some light and could be star boosted. And of course we could star boost this whole arrangement, probably with individual polar statites into whatever spectrum we liked, including one matching our own. The M5 card galaxy would be about 8 times brighter than the M9 version, and have roughly 8 times the habitable area if we imagine it as a simplified Dyson sphere, but would also burn through its stars in about 1/8 the time. Our M5 card would have a lifetime of 1 to 2 trillion years, whereas the M9 card galaxy would exist for more like 8 to 12 trillion. and time might get even a little longer here, as this denser arrangement has even slower passage of time from general relativity, 5 to 6% slower than normal, a small percent but a big number, several times longer than our universe has existed. A cold galaxy made of greater mass, say from the combined Milky Way and Andromeda galaxy, plus the other close galaxies, might run even slower yet. This need not be a full galactic mass either. A compact artificial red dwarf cluster or cold cluster of perhaps a mere billion solar masses would be around a tenth as wide. There's many ways you might harvest this energy and dwell in and around it, and likely you would have plenty of objects inside this packed cluster of red dwarfs. But by default, we would imagine a hazy shell around it akin to the classic Dyson swarm of space habitats, and note that all of these are within a light year of each other for the M9 Card galaxy, 2 light years for the M5, and for any smaller card cluster, light months or even days. This makes a unified empire quite plausible, and one that is of full K3 grandiosity, many billions of times more living room and energy than a Dyson swarm, and many billions of times the living room and energies of Earth, all crammed into a few cubic light years or less. No-FTL civilizations, patience and proliferation. When we imagine a civilization spreading across the galaxy without faster-than-light travel, the first word that comes to mind is patience. Colonizing the stars without warp drives or wormholes means embracing timescales measured not in centuries, but in millions of years, and yet for a Kardashev Type 3 civilization, that patience can yield a harvest far greater than any warp-capable empire might achieve. The No-FTL path to Type 3 does not resemble a single unified civilization. It resembles a meta-civilization, a sprawling patchwork of colonies, cultures, machines, and minds slowly diffusing through the stars. Each new system is settled by ships traveling at a fraction of light speed, and while communication back to the homeworld may take thousands of years, these colonies are not outposts, they are seeds. Given enough time, they don't just survive, they thrive. They build their own Dyson swarms, mine their own planets, create their own art and philosophy, and they send out their own probes and colony ships, repeating the process endlessly, a slow-motion wave of technological life rolling outward into the darkness. Instead of a galaxy-spanning empire, you get a galaxy filled with civilizations, independent but not isolated. Communication networks may stretch across the stars via lasers, or even ultra-long baseline neutrino relays or gravitational lensing stations. Information can still travel, even if it takes centuries or millennia to get there. Think of it as a galactic internet with very long loading times, and an archive that never forgets. Autonomy is the key in this kind of civilization. There's no central government, no capital planet issuing edicts across light years. Though individual systems may host empires dwarfing anything Earth's ever had. Instead, coordination happens through consensus protocols, long-term planning AIs, or shared cultural frameworks passed along by the slow chain of migration and messages. One region may be dedicated to computation, vast computronium clouds converting entire nebulae into mind stuff. Another may focus on ecological preservation, seeding life on new worlds and watching it evolve over geological time. Still others may dwell in tight-packed megastructures, like card clusters, harvesting and hoarding energy across eons. To such a sprawling K3 meta-civilization, even mighty minds like M-brains, computer minds fueled by an entire star, are just one small dot in a larger landscape. And yet, even without FTL, there is unity, of purpose, of origin, of memory. The people of such a civilization may live thousands of light years apart, but they still remember the same homeworld, the same great journey, and perhaps the same guiding principles. Time becomes their medium, not their obstacle. It is also a civilization that is extraordinarily robust. There is no single point of failure, no galactic core whose collapse would shatter everything. If a system falls to entropy, war, or natural disaster, it is mourned, but not catastrophic. Others persist. Redundancy and decentralization are its survival strategy. More than that, this patient mode of expansion allows for a level of care and precision that a fast-moving empire might never match. A no-FTL K3 civilization has the luxury of terraforming worlds slowly, adapting each system to its needs over millennia. It can think in terms of optimal positioning for Dyson swarms, long-range energy relay routes, and staggered population growth, all without rushing. It's not a sprint, it's a bloom. This kind of civilization doesn't just expand, it unfolds, slowly, steadily, inevitably, and when the last corner of the galaxy is finally reached, perhaps after 100 million years, it will not be as a conqueror, but as a gardener. And yet such a conquest might one day come, or even begin from the outset, as vast efforts may begin seeking to collapse this galaxy into one small, compact, and brilliant empire, the Card Galaxy we discussed, and it might seek to spread itself even beyond that range, to gather in other galaxies. Moving the stars. A civilization that wants to control its galaxy must eventually decide whether to move the stars themselves, and while that might sound like an act of divine hubris, it's surprisingly feasible for a sufficiently advanced culture, especially one chasing the efficiency, order, and cohesion needed to operate across tens of thousands of light years. There are many reasons to move stars. Some are practical, to prevent catastrophic collisions, direct supernovae, or clear dangerous radiation zones. Others are aspirational, to create megastructures, stellar clusters, or optimal communication lattices. And some motivations are truly grand, like reshaping a spiral galaxy into a tightly bound stellar swarm for ease of travel and coordination, or to launch part of your civilization to another galaxy altogether, even to bring a galaxy home. The simplest method is also the slowest, the Shikata thruster, a stellar engine made by placing a large mirror in orbit around a star to reflect its light in a single direction. The momentum imbalance gently pushes the star in the opposite direction. While conceptually straightforward, the thrust is feeble, on the order of nanometers per second squared, but over millions or billions of years, even this can move stars across light years. Low-mass stars like red dwarfs are especially well suited to intergalactic travel, as they live for trillions of years and burn fuel with glacial slowness. Bigger ones can accelerate far faster though, as much as 1,000,000 times faster. A more energetic approach is the Helios drive, a scaled-up variant of starlifting. Instead of just collecting stellar material, the Helios drive directs plasma out of the pores of a star, then deflects one jet downward to produce thrust. This turns the star into a fusion rocket, trading away some longevity for vastly increased acceleration. Given enough time, a Helios-driven red dwarf could reach a sizable fraction of light speed, and might do so while towing a small fleet of habitats or planetoids in its wake. But for the fastest and most powerful propulsion, civilizations might abandon the stars in favor of dead stars. A nova drive, powered by controlled nuclear detonations on a white dwarf, can deliver immense pulses of thrust. Its bigger cousin, the supernova drive, could theoretically hurl tremendous mass with explosive force, though the engineering challenge of containing and shaping that blast is staggering. The most exotic option, however, is the quasar drive, a method that exploits black holes as engines. This operates similar to the quasar cannon that we looked at in our episode on black hole technologies. A Kugelblitz black hole, small artificial ones that emit hockey radiation on useful timelines, have their own uses, but I'm dubious if they can be made. However, big or small, black holes are relatively low-tech to gain power or starship thrust from. By feeding matter into a spinning black hole in a controlled manner, you can create an accretion disk that emits radiation with incredible efficiency, even beyond fusion. This method could in theory push entire star clusters or megastructures at relativistic speeds, and unlike stars, stellar mass black holes don't burn out, they simply grow as you feed them mass. With enough fuel, a quasar drive could power a civilization's expansion across intergalactic distances, while its onboard time dilation slows subjective time for its passengers. All of these star drives and more are explained in our episode The Megastructure Compendium. Whether you're nudging a single star, accelerating a stellar arc to another galaxy, or steering a fleet of red dwarfs through interstellar space, the ability to move stars grants a civilization profound agency, not just over its systems, but over the very layout of the galaxy itself. Rearranging galaxies and superclusters. In the long arc of cosmic time, the galaxies are not standing still. Thanks to the expansion of the universe, anything not gravitationally bound to us is drifting away, and the farther it is, the faster it's receding. This is the Hubble expansion at work, and presents a unique problem for any civilization with truly long-term ambitions. Our own Laniakea supercluster, a gravitationally coherent region containing the Milky Way and Andromeda, stretches roughly 520 million light-years in diameter. On its outskirts, galaxies are seen from us at about 3.7% the speed of light, or 11,000 kilometers per second, due solely to the Hubble flow, and just beyond that, faster and faster, up to about 10% of light speed by 1.4 billion light-years away. Eventually, the universe slips past the cosmological event horizon, a boundary beyond which space expands too fast for light or anything else to ever reach us again. This means that even a Type 3 civilization, capable of harnessing entire galaxies' worth of energy, is working against the clock. If you want to preserve access to stars and matter now within your light cone, you must act before they drift beyond your reach. In our episode Fleet of Stars, we explored how civilizations might go from moving entire stars, using the methods we discussed earlier, to an even grander vision, moving entire galaxies, and eventually restructuring superclusters. One strategy is intergalactic migration and galactic merger engineering. Through traditional, if slow colonization, or through automated probes, you settle or secure a distant galaxy, and then use those stellar propulsion systems to tow stars, clusters, even whole galaxies into gravitationally bound clusters. Rather than watching these resources drift away forever, a civilization could actively reel them in, compacting usable mass into megaclusters for long-term security and centralized utility. We call this horizon herding, capturing what would otherwise be lost to cosmic acceleration. How far could we go with this? Is it plausible we could send a spaceship at near light speed to a galaxy, and assuming it is uninhabited, and that folks settling it or the AI gathering it were reliable, we could send it back here, although not at such high speeds, I imagine. Star drives relying on fusion, from the Shkata thruster to the Nova drive, have a hard time getting much over 10% of light speed, and we use most of the mass of that galaxy doing so, and so if we head toward a galaxy 1.3 billion light-years away, at 90% of light speed, we would get there in about 1.44 billion years, but would actually have moved about 120 million light-years further away from us by then, and it might take you about 1.6 billion years to have reached it and spread your collectors through it. You now have a long period of working to get up to speed too, and are going to need to get it going at least 15% of light speed if you want to not only get that galaxy back here, faster than the Hubble expansion takes it away, but before all those stars in it burn out, as your effective speed here is only about 3% of light speed, fighting that rising Hubble expansion, and you're going to be taking around 40 billion years to bring that home now. And you also need to slow down at the end, which Hubble expansion helps with, but the slower your return velocity, the cheaper it is to stop. That's more or less your upper limit for any fusion-based effort. Within that range, you're looking at a few million large galaxies and around 10 times many dwarf galaxies, amounting to a total of roughly 200 to 300 quadrillion solar masses. It's well worth going as far as you can too, since the number of galaxies rises with the cube of distance. If you can harvest galaxies twice as far away, you're gaining 8 times the mass, even if a fair chunk of it gets expended as propellant and takes half of forever to arrive. Even if half the efforts fail or go rogue, deciding not to return, and even then you have at least the contentment of having seeded life someplace, even if it will disappear from our sight. This shepherding process could take longer if you're thoroughly checking whether the stars or galaxies you're reaching are inhabited, also depend on the extent of your ethical lines in the sand. Do you only leave alone systems with intelligent life, or anything with microbes or in between, and do you spare the planet or the whole system, or the whole local bubble of fewer light years around? And mind you, you could just leave that star system or bring it with you anyway, you just need to bring in external propellant for it. A non-trivial task, but not a huge one at this scale. Also keep in mind that some planet you're dragging along on a 2 billion year trip might have just had lichen or algae emerge on it and be launching its own spaceships by the time you arrive. Quasar drives offer even better returns, converting around 20 to 40% of mass into energy, compared to just about 1% for fusion. That translates to 4.5 to 6.3 times the speed, and access to 90 to 250 times many galaxies and mass. At the high end, you might gather as much as 75 quintillion solar masses, though you'd be likely to burn at least half of that as propellant. But here we start to hit size limits again. The event horizon for an object, or cloud of objects, of about half that mass, 30 to 40 quintillion solar masses, is around 10 million light years. That's the domain of a black hole-based economy, which we'll return to shortly. By contrast, our more conservative estimate, returning perhaps 100 quadrillion solar masses via fusion, could be packed into a region just 30,000 light-years in radius. That's about the same distance we are from the center of the Milky Way. Both scenarios would represent Kardashev Type 4 civilizations, operating at supercluster scales of power, though one is vastly larger in both energy and mass. Much as we can imagine FTL civilizations, we'd also envision ones that have found ways to neutralize gravity entirely, and frankly, I would consider that more likely. So this might not represent the absolute maximum size for a civilization. Still, somewhere between 1,000 and 1 million galactic masses, you're likely to hit a practical ceiling, where sheer size begins to hinder you again, particularly due to communication lag. As your power usage grows, so too must the surface area of your civilization, since you have to radiate away all the waste heat. If you want 100 times the power output, you need to be 10 times wider, but it also means your energy density drops by a factor of 10, because your volume increases by a factor of 1,000, while your power only goes up 100-fold. Our original M5 card Galaxy design had a radius about 1 light-year. If you scaled it up to 30,000 light-years, you could handle roughly 1 billion times more power, but your civilization becomes 30,000 times less dense. That's still far denser than any natural galaxy though, despite being smaller in total volume, and now you're working with 10 to the 45th watts of usable power, which puts you firmly in Kardashev Type 4 territory. However, by the modified Sagan scale or MSS that we use on this channel, detailed in our Kardashev scale and population episode, this would actually rank as a K3.9 civilization. On the MSS, K1 is 10 to the 10 megawatts, K2 is 10 to the 20 megawatts, K3 is 10 to the 30 megawatts, and K4 is 10 to the 40 megawatts. So a 10 to the 45 watt empire, or 10 to 39 megawatts, will clock in as a K3.9. Using megawatts and the MSS scale just makes it easier to track these incremental steps. A full Dyson swarm around our Sun, which is brighter than most stars at about 4 times 10 to the 20 megawatts, would qualify as a 4K2.0 civilization, whereas Proxima Centauri at 7 times 10 to the 17 megawatts would support a 7K1.7 civ, or rounded up a K1.8. Once we start about moving from K3 civilizations to K4, and without faster night travel, these projects span billions of years. But with enough time and foresight, the very structure of the local universe can be transformed. Over eons, individual galaxies become building blocks for artificial superclusters, strategically reshaped to retain resources, reduce isolation, and compress civilizations into tightly bound pockets of cosmic infrastructure. And once you're dealing with that scale, it may no longer be appropriate to think in terms of Dyson swarms or Birch planets. You might be thinking in terms of Dyson filaments, strings of galaxies aligned by intent, or computational walls, where matter is reorganized not for habitation, but for universal simulation or entropy management. To a Type 3 or 4 civilization, the universe is not a playground, it is a perishable resource, one they can watch slip away or take bold and godlike steps to conserve, and for such civilizations, fusion and the stellar era are dangerously inefficient. Today we're talking about ways not just to terraform whole worlds, but how to change around whole galaxies if needed, and to alter stars to be in brightness and wavelength more suited for life, at least for terrestrial life. But there may be alien biospheres that developed where no sun shines, and this month's Nebula exclusive, Dark Biospheres, we explore everything from life on rogue planets in the void far from the sun, to planets so close to their sun they tidally lock and have one side in perpetual darkness, where life might still thrive deep below the ice. Nebula is the largest creator-owned streaming platform out there that we founded back in 2019, and I've been putting exclusive bonus episodes and extended editions there since the beginning, and for the last few years, we've released a new full-length episode there the first of every month. There's dozens of exclusive SFIA episodes posted there, along with more bonus content from myself and many other creators, and every episode of SFIA is available there days before it comes out anywhere else, and without any ads, including this one. Just great content from myself and many others, and you can get access to all of it by joining today for just $36 a year or $3 a month. That's 40% off. Head to go.nebula.tv/IsaacArthur and start watching today. Black holes as galactic waypoints and interstellar hubs. Black holes are more than gravitational anomalies or power sources. They are strategic locations. In a galaxy-spanning civilization, especially when operating without faster night travel, The ability to accelerate or decelerate spacecraft becomes paramount. Black holes, with their intense gravitational fields, serve as natural slingshots, allowing ships to shed or gain velocity with enormous efficiency, as well as change directions for free. Pairing them, letting a ship whip around one and break around another, gives interstellar travelers tools to trim centuries off a journey or to stop where other braking methods would be too costly. Binary black holes are even better as waypoints, but pretty rare. Same for a binary of a black hole and a neutron star. Such ships can be sent at very high speeds using powerful pushing beams fueled by stars, but black holes can provide even greater power, with higher efficiency and throttle control to produce only what's needed. As a result, they may feature vast beaming arrays linking them to neighboring stars and forming a wider interstellar laser highway grid between black holes, a megastructure akin to our own highway system, but scaled up to galactic proportions. And because they are deep gravitational wells and immense energy output via accretion disks or frame dragging effects, they make natural sites for infrastructure, fueling stations, communication hubs, megastructure anchors, and informational vaults. Each black hole becomes a kind of sector node, potentially servicing tens of thousands of star systems, and quite probably the first point of arrival, as you can use them for a lot of free braking from very high speeds, letting ships zoom to that region of the galaxy faster than they could to a neighboring star, because they need less fuel to slow. There may be 100 million stellar mass black holes in our galaxy, meaning each one could represent a capital for a region roughly 10,000 stars in size. Even without fast light communication, signal lag would have to be limited to centuries, short enough to maintain a coherent, if very loose regional government or cultural identity. Especially if your citizens are ultra long-lived for advanced life extension or are otherwise post-human. These black hole bubble civilizations might be little islands of civilization in a broader and looser galactic landscape, especially if it turned out to be impractical to maintain cohesion away from one by more than, say, 25 light years, leaving everyone else more of a hinterland. In that sense, black holes don't merely support interstellar travel, they define its logistics and become its keystones. Some might even become the first cities of a new spiral arm, expanding outward like the Roman roads once did from old capitals. They're not just cosmic curiosities, they're the load-bearing pillars of galactic infrastructure. They can also be truly enormous in their own right, as the smallest natural black holes are about 3 solar masses, 1,000,000 times Earth's mass, and you could construct a shellboard around one that had normal Earth gravity on its surface, but 1,000,000 times the living area, and all the power needed to run that, by slowly dropping matter down into the black hole, and as a result is in a very natural position to be claiming its role as a capital of a galactic sector. Trantor and Coruscant eat your hearts out. This is a mega-Earth, in a very literal sense, as we discussed in our episode, Mega-Earths. Birch Planets, the final No-FTL civilization. We can go far beyond modest megaplanets around stellar mass black holes, and if we do, we arrive at perhaps the most extreme megastructure ever conceived, the Birch Planet. Originally proposed by the late great engineer and physicist Paul Birch, who also gave us the orbital ring and methods for terraforming Venus, this idea envisions not just building around a black hole, but using its gravity to support entire layers of civilization stacked atop one another. A typical Birch planet would be constructed around a supermassive black hole, like the one at the heart of the Milky Way. That object has a mass of 4.5 million suns, or about 1.5 trillion Earths. That means a single spherical shell around it, at the radius where gravity equals Earth's surface gravity, has 1.5 trillion times the surface area of Earth. Living area of the same gravity on a spherical shell rises linearly with mass, and unlike a Dyson sphere, which must sit millions of kilometers from a luminous burning star, a Birch planet could have dozens, hundreds, or even thousands of these shells layered atop one another. They may be able to get around the normal waste heat issue of multi-layer shell worlds too, as dumping infrared waste heat into a black hole by reflecting it might get around the normal thermodynamic restrictions. Each shell represents another Earth-like surface, times a trillion, supported by active structures and powered by the gravity of the black hole itself. This scale produces living space beyond imagination, and contiguous too. Even the shell layers can be connected by spiraling landscapes, allowing you to walk, swim, or fly between every piece of it. A mere dozen layers would offer the surface area of 20 trillion Earths. 1,000 layers? That's a Kardashev Type 3 civilization's worth of living room, all within a light hour's commute. Unlike a sprawling galactic empire, it's intensely concentrated. Even in its most extreme form, a black hole of 1.55 trillion solar masses, potentially including dark matter, with surface gravity equal to Earth's, you are still talking about a structure just 1 light year wide. Each shell provides a living area of 516 quadrillion Earths, and as you move outward, that only increases. Though gravity diminishes with distance, at this scale, even layers spaced hundreds of millions of miles apart would experience only trivial differences in surface gravity. That's how vast a maximum scale Birch Planet truly is. Information can cross the entire construct in under a year, enabling real-time governance, trade, and cultural cohesion for a civilization potentially housing billions of billions of billions of people. No light lag between systems, no fragmentation around the stars, a unified super-civilization in a single titanic construct, outnumbering us a quintillion to 1. Time dilation adds another benefit. Near the lower layers, time slows drastically. A resident of Layer 10 could visit Layer 1000 and return to find the calendar above barely moved, making Birch Planets ideal for long-term planning, computation, or shelter from cosmic threats. The deepest levels might function as temporal bunkers, safe from both entropy and external upheaval. I cannot even imagine what it would take to invade such a place, and destroying it would serve no sane purpose and likely be nigh impossible too. Again, there is a natural upper limit to Birch Planets. A black hole with 500 quadrillion times Earth's mass has an event horizon 1 light year in diameter, with surface gravity equal to Earth's. Beyond that size, any shell would lie inside the event horizon and cease to be usable. Indeed, with frame dragging concerns, you might need to stay even lower mass, though your black hole does not need to be rotating to cause frame drag, except this is part of how we generate power off of one. This sets a hard boundary on how big such a structure can get under known physics, an ultimate capstone on megastructure engineering of a single Earth-like superplanet. While vast in scope, this upper limit also implies a kind of closure. A civilization that builds such a structure has likely harvested its entire galaxy, even some neighbors, and has nowhere else left to expand. It is not just the most massive habitat possible, it's the final, complete expression of a civilization's turn inward, seeking unity, permanence, and control in a universe otherwise racing toward entropy. And that's the other function of a Birch Planet. Much like artificially compactified galaxies, it solves the divergence problem. In a normal Kardashev 3 empire, it might take millions of years to settle a galaxy, and the colonies on the opposite ends might be more alien to each other than we are to trilobites. But by compressing the civilization to one location, communication stays practical, identity remains intact. You have a single empire, not a million echoing fragments of a long-dead species. Not that it's likely to be super uniform, given that Earth is not. It may have countless nations on it, but some degree of meaningful uniformity is possible, and for baseline humanity too. We do not have to limit ourselves to only contemplate massive megaminds using stars as their engines that are part of some galactic civilization of a few hundred billion M-brains. It's also a near-perfect hiding place. Birch Planets are not covert in construction. Gathering and reshaping entire galaxies worth of matter is not subtle, but once complete, they are easy to miss. All the heat and light is redshifted by proximity to the event horizon. Their waste heat might be dumped into the black hole entirely. Their size, while vast, is tiny compared to a whole galaxy. If you're not looking directly at one, you would miss it, and if you are on one, there's little reason to look out. You've already harvested the universe. The outside is just noise. Birch Planets are not exactly stealthy if you're trying to hide from parallel civilizations, but they could still be out there, floating in the apparent emptiness where a galaxy used to be, and we might easily miss them. Normally a K3 or near K4 civilization, loud, grabby aliens, would be impossible to overlook, even from a billion light years away with modern astronomical instruments. But a Birch Planet concentrates its emissions, redshifts its light, and may even dump its waste heat into a black hole, or most of it. It doesn't need to be silent, just hard to notice. And if it took 1,000,000 years to go from us, now, to building one, that's a fairly short time in universe terms. Even if it were happening to every galaxy, only 1 in 1,000 would be visible in the process of building one, at most, so easy to miss, at least for us. Whether for power, population, unity, or obscurity, the Birch Planet represents a natural terminus for galactic ambition, not an empire among the stars, but a single staggering construct that is the Empire, compressed into a globe of quiet infinity, not just the final step of infrastructure, but perhaps the last word in civilization itself. It is also something that could be built without a human or human-level intelligence ever leaving your homeworld or home system. There's nothing ultra-complicated about grabbing resources, or even moving stars, that even modern AI could not do. This idea fits neatly with the concept of an interdiction bubble civilization, or IBC, a civilization that believes its distant interstellar colonies will inevitably diverge to the point of becoming alien and possibly hostile. Seeing little long-term profit from trade or shared research beyond its immediate stellar neighborhood, perhaps a radius of only a few light years, it adopts a strategy of containment and control. It strip mines surrounding systems, rendering them incapable of supporting potential rivals, and turns itself into a kind of fortress oasis. The harvested resources are brought home, while the surrounding region is left a barren desert, intentionally emptied of anything that could threaten the core. In this case, they probably start by building a Matryoshka shell world around their original home planet and just keep adding layers, until the planet becomes geocentric, with the Sun as Dyson Swarm effectively orbiting it. Over time, they continue expanding, replacing older inner layers with material brought in from gas giants, and eventually centering the entire structure around an artificial black hole. All the hydrogen and helium they collect gets fed into the black hole, while rocky material is used to build new layers around it. Stars can be disassembled through star lifting, see our episode on that topic, and your Birch Planet or compact artificial red dwarf galaxy does not need to be centered on your natural galactic core. You can simply keep expanding your homeworld, evolving that initial Dyson swarm into a Birch Planet or a cold cluster, then into an artificial galaxy, and all the while, robotic systems can be quietly harvesting the rest of the universe to bring home. Faster-than-light civilizations, beyond the light barrier. So far we've explored the universe as it is, finite in its speeds, expanding in its boundaries, and anchored to the laws of reality. But what if those limits aren't final? What if some civilizations discover a way to go faster than light? In science fiction, FTL is the great enabler. It's the bridge across the stars, the shortcut to a unified empire. It allows real-time communication, centralized governance, rapid military response, and interstellar commerce. And in a Type 3 civilization, the ability to bend space and time might be the only thing that keeps such a sprawling empire from falling apart. But fast light travel isn't a single solution, it's a spectrum of possibilities. You might have warp drives like the Alcubierre warp drive, or hyperspace routes accessed through alternate topologies, or perhaps the most versatile of all, and our last galactic megastructure for today, wormhole networks, what we might call stargates. As we explored in our Stargates episode, wormhole-based networks allow for permanent or semi-permanent connections between distant points in space, and potentially in time or between universes. These portals could be engineered by stabilized micro-black holes, exotic matter, or natural cosmic wormholes seeded during the birth of the universe. The implications are staggering. In one model, wormholes might be massive installations, orbited like stars, fed mass and energy like reactors, and stabilized with exotic matter. People tend not to realize the classic wormhole, or Einstein-Rosen bridge, discussed in sci-fi a lot, tends to require more mass to build than a star. There are some lower mass options that have been theorized, see our wormholes episode for those, but otherwise that's a lot of mass, which means you're probably not getting several of them per star system, or even one. A galaxy-spanning wormhole network might consist of millions of such hubs, each linking clusters of systems with near instantaneous travel. A K3 civilization could distribute these like rail lines through the stars, fewer spaceships, more trains and cargo tubes through cosmic tunnels. You might even make the smaller, though still huge effort, of compactifying nearby stars to be closer to the nearest wormhole. Classic wormholes are neither instantaneous nor capable of enabling real-time communication across the galaxy, at least not in the way we enjoy here on Earth. However, they could still support civilizations operating on timescales we see with Birch Planets or called Galaxies, and in fact, they complement those structures well. Wormholes also allow expansion deeper into the universe, even if the initial trips must be made at sublight speeds. You may have to create the two wormhole mouths together, the entrance and exit, and drag one with you to your final destination, but that still allows a colonization range of several billion light years. And because bandwidth matters, such portals wouldn't just send people, they would transmit materials, energy, even control signals for machines. In one scenario, entire civilizations could run server farms and habitats light years apart, but networked via wormholes so tightly they function as a unified computer or city. Others might use stargates to terraform distant worlds by linking them to habitable ones, transferring atmosphere, water, or even sunlight through planetary-scale conduits. It all depends on how small and easily you can make one. Drop a wormhole in the sun and one in orbit of an icy planet and bingo, geocentric fake sun. Also makes a nice spaceship drive. Of course, the physics of wormholes brings up huge constraints. Time dilation, causality issues, exotic matter requirements, and the ever-present risk of turning a traversable wormhole into a black hole. But as we discussed in Stargates, there are plausible workarounds, one-way channels, time separation to prevent paradoxes, or simply accepting high-mass constructs as the cost of galactic cohesion. And the structure of such a network is itself fascinating. If you limit wormholes to a single gate per planet, a la the Stargate franchise, you get a tiered civilization. Each world connects to only a few others, dialing up a different one every hour over, say, the course of a week, creating layers of connectivity and political centralization. But if your wormholes are cheap and ubiquitous, you get a far more anarchic and decentralized civilization, with countless worlds forming a true wormhole web, a cosmic internet routing matter and data as easily as we browse the web today. And then there are the wild cards, wormholes to parallel universes, gates that draw energy from younger or hotter realities, portals anchored outside the observable universe entirely. In such models, a K3 or K4 civilization may not just span space, but bridge into realms untouched by entropy or constrained by known physics. So whether through warp fields, hyperspace corridors, or galaxy-spanning stargates, fast light travel transforms the map of possibility. A Type 3 civilization with FTL might not just reach the galaxy, it might remake it, turning distance into irrelevance and time into a design choice. Still, the question remains, is it always desirable? Because where patience breeds resilience and divergence fosters creativity, FTL brings unity, but also fragility. Problems and enemies can spread faster than light too, and in the end, whether light takes years or seconds to cross the stars, the challenge isn't one of speed, it's one of sustainability and wisdom. A Type 3 civilization may command the power of a galaxy, but the real challenge isn't capturing starlight, it's in using it wisely. Even assuming a baseline human population, we can estimate energy needs at a megawatt per person, or less. That means a civilization could support more individuals than there are grains of sand on Earth, and do so for trillions or even quadrillions of years. Post-human civilizations can take this even further. Imagine a billion-citizen empire where each citizen is a vast computer mind built around a black hole. Such civilizations could conduct more research in a moment than all of humanity has in a millennia, and if there are ways to reverse entropy, travel superluminally, draw power from other universes, or alter gravity, they've likely discovered them. They might build galactic-scale structures not just to harness dark energy, but to halt local Hubble expansion, draw galaxies inward without ever launching a ship, breach new regions of the multiverse, or even spawn entirely new universes or realities. Across this episode, we've explored civilizations that span light years, move stars like pawns, and gather galaxies before the universe carries them away. Some expand outward with patient precision, others turn inward, compressing all they are into titanic constructs of unity and endurance. But for all their power, they still wrestle with the same questions we do. How do you stay together across vast distances and longer times? How do you endure eternity and immensity without losing yourself in them? And what do you build when you already have everything? In the end, Whether spread across 100 billion stars or stacked into a single planet-wide shell, perhaps the mark of a truly advanced civilization isn't how much energy it uses, but how much purpose it gives to that energy. As always, and until next time, thanks for watching, and have a great week.